So, I'm Nicole White, and I'm a data scientist at Neo4j, and today I'm going to be talking about querying your graph with Cypher, obviously. And I know you've seen a lot of Cypher already today, and especially at the training yesterday, but I'm going to go into a little bit more detail, and we're going to walk through some Cypher queries together. I'm going to highlight my personal favorite things about Cypher, having come from SQL a while back. So this is the example data set that we're going to be working with for the next 30 minutes. It is Dallas-Fort Worth Airport, places in Dallas-Fort Worth Airport, and what gate and what terminal they're at. And then we also have simulated some users. So pretend we have like an app where users are liking and checking into these places. So here, obviously I'm in the Neo4j browser. We have a few different nodes here. We have user nodes that have a name property. And like I said, these users can like or check into places. They can both like and check into places, or they can just do one of those things. All these places are in a category of some sort. And then we model which gate they're at by pointing to a gate node. And then we know that this gate is in terminal E by pointing to a terminal node. And users can be friends with other users with a friends with relationship. And we also have a property on this liked relationship. It is a numeric property. It's a score. So when someone likes a place, they give it a score, hypothetically, right? So this is the data set that we're working with. And let's just get started. So as you know, you're pretty much drawing the graph pattern that you want to query for. So when you want to ask for a node, you're going to wrap it in parentheses. And most likely you want to specify a node label. And this C here is the identifier, right? So here we're going to get all of the category names in our graph. And the identifier can be whatever you want. It's simply a variable that you refer to in the return clause. And most likely, though, you'll be wanting to draw a graph pattern. So a pattern is going to consist of at least a node relationship node. So here we have a node, starting node on the left, where we've decided it's going to be a place node. Cursor. Well, it's a place node that has an outgoing in category relationship to a category node. And then we have a where clause, just like in SQL, to say that the name property on that category node has to be barbecue. And then we're returning the name property off of the place node as barbecue. And you'll notice that if you've worked with the browser, that when you ask for a property back with Cypher, you're going to get this table. But if you simply ask for the entity itself, let's get both of them, you're going to get a picture, right, a graph result. So that is an important distinction in Cypher. When you're asking for the entire entity, you're going to get all the information back, whereas if you specify a property, you're going to get your nice table, of course. And if you don't like the where clause for whatever reason, you can use shorthand conditioning. So here, this is the same exact query, except instead of using the where clause, we've actually wrapped that up into the match clause itself, and we've used curly braces to say that the name property on that category node has to be this string, right? So this is going to be the same exact result, and that's just a matter of preference. Some people like to put everything in the where clause because it reads a little bit cleaner in the match clause, right? And of course, you can build several paths in the match clause. So you can do node relationship node, node relationship node for as long as you want. And you can separate that by commas in the match clause. So here, we're starting again at a place node that has an outgoing in category relationship to a category node. And then from that same place, notice that we've bound the node up here to P, the identifier P, and then we're referring to that same identifier down here on the second line of the match clause, and then saying, okay, now I want to traverse the at-gate relationship to the gate node that it points to. And again, we're only going to look at the the barbecue places in Dallas-Fort Worth Airport. And of course, you can return multiple columns. So here we've separated that by a comma. We're now returning the number property off of the gate node. So this is going to give us the names of those barbecue places and the gate number. More likely, though, you'll want to see which terminal that gate is in, because it's good to differentiate between gate 18 in terminal A versus gate 18 in terminal B. So again, you would just throw a comma in there, move to the next line in the match clause, and now, again, you're carrying over that identifier. That identifier G right here that we defined in this line, we'll use in the next line to say, now I want to traverse the InTerminal relationship out to the terminal node. And that will now give us the terminal that all of these barbecue places are in. So bringing all that together, we can start doing some more recommendation type stuff. So if we want the closest coffee place to gate 10 in terminal B, we'd have the match clause that we've already seen so far. And then we're going to throw a few conditionals in the where clause. We're going to say that the category name has to be coffee, and the name of the terminal has to be B. And then, of course, in Cypher, you have all of the mathematical functions that you would expect, absolute value, max, min, sum, average. This is just one example. So here, we're returning the absolute value between the gate and the number 10, because we don't care if we have to turn left or if we have to turn right. When we want to find the closest coffee place. So here we're returning the name of the place, the absolute value of the gate number minus 10 as the distance that we'll have to walk to this coffee place, the gate number, the terminal name, and we're going to order by the distance because we want to see the closest ones first. So of course, Cypher has order by and limit, as you would expect from any query language. So now we know that we will only have to walk 2 gates down to gate 8 in terminal B, and we'd have to go to Starbucks. Or we could walk one more gate if you prefer Dunkin' Donuts. So aggregation is, of course, very straightforward in Cypher. There's no group by statement. It simply will group by it for you, depending on the order you pass it to the return clause. And of course, here we want a count per category. So you can count star, just like you would count star in SQL. So here we're matching the place in category pattern, and then returning the name of the category, and then the count of how many of those patterns exist for that category name, right? So this is going to give us all the categories and how many places are in those categories. And of course, you could order by that count, which would make more sense for this kind of query. And then usually people want to know at this point how they can only keep categories with a certain amount of places attached to them, and you can do that with the with clause in Cypher. It's kind of like having in SQL. So here, the same thing, we're matching places in categories, and then we've replaced the return clause with a with here, and it's kind of saying, with these things, now do this. So here we're saying, with the category name and the count of how many places are in that category, we then say in the where clause that that count has to be greater than 5. And so that is how you would do something like that. If you want to filter on any aggregations, anything that you can't declare in a match clause, like a count like this, you have to infer it with the with clause, and then you can move on to filtering out things that do not meet your criteria. So here we are only keeping places that have more than, or only keeping categories that have more than 5 places, and returning the category and the places, right? And so here we've aliased in the with clause, and then referring to those aliases in the return clause. So this is one of my favorite things about Cypher is negating patterns in the where clause. So this is, well, there's probably some more there's probably some examples of times when you'd want to put a regular pattern in the where clause, but I usually only use it for negating patterns. So here we're finding places that Alice has liked but not checked into. So here in the match, the original match clause at the top is pretty straightforward. We're matching on a user node with an outgoing liked relationship to a place node where the name of that user node has to be this string Alice. And then we're saying and not this pattern. So this pattern cannot exist from Alice to that place. So there cannot be a checked into relationship between Alice and that place, which is a very helpful thing to be able to specify, which we'll see later in a recommendation query. So here, clearly, we're only getting the places that Alice has liked, and of course, there's no checked into relationships to these places. Another great thing about Cypher is that you can use a type of OR with relationship types. So here we're matching on fast food places that Alice has liked or checked into. So here we are using the pipe in the relationship type here in the square brackets. And we're saying that Alice, the user, has either liked or checked into a place, and then we're getting the category of that place, because then we would then want to say that the name of that user has to be Alice and the name of that category has to be fast food, because we wanted fast food places that Alice has either liked or checked into. So here, we should get some more results. Here we've got places that Alice has liked or checked into. And then, of course, we only got the places that are in the fast food category. Okay, so let's combine some of the things that we've just seen into a recommendation query. So here, remember that all of our users had friends in this example app. So here we are recommending fast food or snack places to Alice based on who she's friends with and their ratings of those places. So here we're matching, we're starting at Alice, and then we're traversing the friends with relationship to another friend. And it's important to note here that I'm leaving the direction off of this friends with relationship. Was anyone at the modeling thing earlier with Ian? Did you talk about bidirectionalness? Okay, well, in Neo4j, everything, by definition, it has to have a direction, but you can treat it as an arbitrary direction and just leave it off when you actually query for it. And so that's how you would treat it as a bidirectional. So here, of course, if I'm friends with you, you have to be friends with me, is usually how it works. So we want to just leave the direction, the arrow rather, off of this because we don't care which way that's going. So here we're matching the friends with relationship either way between Alice and another user. And then we're getting all of the places that her friends have liked. So here we've set this identifier friend, and then we're using that identifier down here in the next line to get all of the places that her friends have liked. And then note that we're also putting an identifier R on that liked relationship because we want to get that score property off of it later, because the score property is stored on that liked relationship. And then finally, we are, from the places that her friends have liked, we're traversing the in-category relationship to a category node because we want to check that the category name is in fast food or desserts and snacks. And then, of course, we want the username to be Alice. And then we also want to say that Alice can't have already liked or checked into that place. We want to recommend places to Alice that she hasn't been or liked or checked into already. So it's very easy with Cypher with both the negating patterns in the where clause and by using the or with relationship types to say, I want to find all these places that my friends have liked, but I have not been to. So here we're saying that the pattern Alice liked or checked into this place cannot exist for these places for that we are about to recommend to her. So now we can just return the name of the place, and then we're going to use the average function, and we're going to pass the score property from, remember we put that identifier R up here on the liked relationship, and we're gonna get the average of that score property as average score, and we're gonna order by average score descending. And so this will show Alice in our example app that she should go to Grove Natural Snacks because her friends, assuming she has similar interests as her friends, have rated that the most highly. And then if you wanted to add a bit more personalization or social aspect to this query, you could use the collect function. So this is the same exact query as earlier. I've just added one more line to the return clause, and here I'm using the collect function, which will, I think in SQL it's kind of like group by concat or something like that, where you would take what would have been rows and you'd bring it up into one row, right? So here for Alice, or for each recommendation of a place, we're collecting the names of the friends who made that recommendation to her. So then we can add a bit more social aspect to that. So here we see, I don't have a lot of data in here, but if there were more, you'd see several friends who had made the recommendation to Alice. So this score, for example, 6.5, is a combination of recommendation from both Forrest and Hank, because they both Forrest and Hank had liked that place, and then we gave her the average score. Okay, so another great thing about Cypher is that you can do variable length path matching. So remember, we have the friends with relationship between users, and you can find who, for example, who do Charles and David know each other through by traversing an arbitrary length of those friends with relationships between the two of them, right? Because Charles and David might not be direct friends with each other, but they might be friends through several other people. And we don't know if it's 1 or 2 or 3 or 4. So here we can pass the asterisks to the, just right after the relationship type, you put the asterisk, and then that's going to traverse an arbitrary amount of those relationships to find Charles on one end and David on the other. So that's going to give us something that looks like this. So we can see that Charles and David are friends with each other in a few ways. They go through Alice and Hank, and then that's one path, and then another path is they go through Alice, Forrest, Elaine, Hank, David. And that's great because, as you know, in SQL, if you wanted to do something like this, you would have a table that has a foreign key to itself, and then you would join it on itself several times, but you have to explicitly say how many times you're joining it on itself. So you can really, it's kind of hard. I mean, you can technically left join and then kind of emulate a variable length path, but that's super expensive, and it's not a friendly syntax either. Of course, you have to copy paste the left join over and over for how many times you want to go out. Especially here, you don't know what the maximum is, but Neo4j will easily find it for you. And then with this, the P identifier here, we actually assigned an entire path to an identifier. Earlier, we were putting, we had only been putting identifiers on nodes and relationships, but you can also assign an entire path to a single identifier P. And then with that identifier, there are functions within Cypher that are specific for working with path objects. So here we're matching, again, we're matching on any amount of friends with relationships between Charles and David, and then we can extract all of, for each of these path objects that's returned, we can extract all of the name properties out of all the nodes on that path. So with the extract function, it'll give you a tabular view, rather, of what's going on, because sometimes it's hard to look at the visual view that the browser gives you and really understand what's going on. Because it's not clear here when you look at the visual result that there were 2 paths found. So here, we're actually going to get a tabular result. So here we are iterating through all of the nodes on the path. So for each x in nodes P, essentially give me the name property off of that node. and then also give me the length of the path. So here we just pass the p to the length function, and that's going to tell us how many steps are in that path. So here, as I showed visually, there are two paths found. One's length 3, one is length 5. One of them has these people on the path, and the other has these people on the path. Of course, more likely, you'll want to put a min and max on this variable length search. So more importantly, you want to put the max because in complicated graphs, it might explode if you search with the asterisks without putting a max on it, because it'll just search forever. So most likely, you want to put a maximum value on this. So the syntax here is min dot dot max, and the default min is 1. So here, we are searching for paths between length 2 and length 4. And remember, the length is the number of steps along the way, not how many nodes, it's number of steps. So here we're searching for paths between length 2 and length 4, which is a much friendlier query for Cypher to figure out. And of course, the path with length 5 was not found because it is too long and did not fit the criteria. And of course, you can do exact length by omitting the min and max syntax. You just specify an integer by itself to ask for an exact length. So this would get an exact length of 5. And so this, of course, will only return us that length 5 path. And finally, another thing that makes my life a lot easier when doing these types of queries is collection predicates along pathways. So if you have some criteria where, okay, yes, I want to find this path, but I want at least one of the nodes or all of the nodes or none of the nodes, I want to assert something for the nodes along the path or the relationships along the path, whatever the use case is, you can use collection predicates like any, none, or all, or single to check for how many nodes is this true. So if we, for some reason, wanted paths between Charles and David through the friends with relationship, and we only wanted paths where Forrest is on the path, we can again use the x in nodes p syntax here to say this has to be true for any of the nodes on this path that the name property is Forrest. So that's a really easy way to throw into the where clause any criteria that you want to assert across all the nodes on the path, which Cypher, of course, makes it very easy to do. And of course, we only get the path that has Forrest on it. Because this here was asking for paths between length 1 and length 5. The default min is 1, so you can just leave it off if that is the case. So that is all my favorite things about Cypher. Does anyone have any questions about Cypher? Specifically, anything that you first?
Yeah, I have a question about the example with the recommendation query. The first one.
The first recommendation, closest coffee place? This one?
Maybe the second one. The one where you recommend places.
This one?
Other people like, yeah. So you would return that name of place and the average score. So my question is, would that return different places with the same name as a whole thing, or as different nodes? I mean, does it get aggregated by place name or not?
This is aggregated by place name. So there's only one Starbucks coffee node in the graph. If I had done it differently, like perhaps Starbucks coffee at gate 7 in terminal B is way better than Starbucks coffee in like terminal A or whatever. So I actually didn't differentiate between the two. So there's only one Starbucks coffee node, and then it points to all the gates of all of its locations, because Starbucks is in multiple spots. But still, with this query, if I did have multiple Starbucks nodes, it would be the same thing. It would still be aggregated by place, because I said that it has to, because that was how the order that returned it in this return clause. So I've returned the name of the place and then the average score. So it's going to group by place name, and it's only going to give me distinct place names.
So what if I wanted the different places, not the same name? Like,
Well, then at that point, you would have to throw something else in there. So perhaps I would actually have to also traverse the, well, I'd have to change my model, first of all. I would have to have separate Starbucks nodes for all the Starbucks, the different actual Starbucks in Dallas-Fort Worth. Or I could return, no, I'd have to change my model, because when people have liked Starbucks, I haven't captured any information about which Starbucks it was, whether it was at gate 7 or at gate 9. So that's a modeling issue that I would have to fix if I wanted to integrate that type of stuff into.
it actually works like a group, like a SQL group line. And it does actually return different things based on the field, not just the node, the actual field.
It's the actual field. Yeah, it's not going to be it's not by node. So if I did have more than one Starbucks coffee place, it would still be, because it's place.name, not place. If I had done it by just place, then that would be a distinct node. Yeah.
For the same problem, what happens when I return not only the place name, but for example the address as well? How will we group this?
Well, that's the same problem. That's a modeling issue in this graph, is that I don't differentiate between two different Starbucks.
It's okay, but what will happen if we group by name and address, or only by name, or
Yeah, so then at that point, we wouldn't really get it wouldn't really make sense. We would have duplicate results.
I don't want to make any sense for that. The question is if I returning not only one property, then for example two.
Yeah, if you replace place.name,
How will we group this average?
then it would give you the distinct results for each of those groupings.
Okay, then
Right, so place.name, so like if we also got the gate number, then we would have a distinct row for each of those, right? And unless we collected it up into one row. The collect function would, like if we wanted still to have a distinct row per place, but also all the addresses of those places, we would have to collect that information up into the same row, like with the collect function that I showed, right? Yeah. Yeah.
I was wondering if you could show an example using something like, for example, I want to query for Charlie's and Charlie, and how this affects the performance.
So what just happened? What? You would use regular expressions. That's what you're talking about with the like. So you would use the equal tilde, and then you use a regular expression to say I want things that match this regular expression. So this is going to match places that are both in the bar and barbecue category, right? So that's the equivalent of a like. Talking about SQL's like? Yeah,
Is
so
there a huge difference in terms of performance?
what's that?
Is there a huge difference in terms of performance when you use the regular expressions instead of?
Yeah, because it's not going to use the index anymore. You'd have to set up a different type of index. Maybe that hasn't changed, hopefully. Maybe Cypher team can comment. I don't think that's changed.
We just heard in the previous presentation that there's going to be like a range index in the future.
Oh,
that will
excellent.
optimize this type of stuff.
That's great news. Yeah, so I'm pretty sure, I don't think it's changed. Last time I checked, the regular expressions don't use the index. So like if you have an index, which of course you would, on the place node for the name property, the index would be used if you did, when you do an exact match like that. But when you use the regular expression, I'm pretty sure it doesn't use the index. Because then you'd have to go on your own and set up the Lucene, the full text search on your own to use that. Any other questions? Yeah.
When you length files of indeterminate length, are loops going to be included in that by default? Or?
Cypher won't traverse the same relationship twice. So like if you had like a triangle of nodes and you said match me length 5 or something, it's not going to keep going. It will just say not found. So yeah, no cycles. It won't.
Would you want to change that then if you wanted to allow loops?
No, you'd have to get kind of hacky about it. So not really. That's the behavior we wanted by default. because otherwise it could get out of control doing cycles. So yeah, you'd have to go in like the Java API to write anything that you wanted to go over the state relationship twice. All right, I think I'm out of time. Thanks, everybody.